welcome to Neat AI. So in the last video, I coded up Flappy Birds and created a standard neural net to get the birds to fly through the pipes. I looked in detail at the steps involved in creating the next generation, discussed the crossover element and mutation features which allowed a population of birds to evolve over time. There were 5 main steps involved, so waiting for all the birds to crash and die, selecting 2 birds at random, creating a new bird from those parents, and how the new bird gets its connection weights randomly from both parents, repeat until the next generation is complete, and finally, mutating the connection weights. And this worked quite well, allowing the birds to eventually find solutions and fly for a long way through the pipes. In this video though, the process becomes more sophisticated and has a couple of extra steps which allows the birds to explore different net structures. These are speciation, which splits the population up into structurally similar groups, determine the number of kids per species, crossover, which is different this time because the parents won't necessarily have the same structure, repeat again until the next generation is complete, mutating the connection weights, and then mutate the structure, and that's done by giving it a small chance of adding new nodes and connections. So first up is speciation, and this is a process that happens for each new generation. A parent is chosen at random from the entire population and assigned to species 1, and its structure is then compared with every other bird in the population. If the differences in their structures is below a certain threshold, then they will be added to species 1 as well. So how does it do the comparison? It simply adds up the connections that are not present in both parents. They are called excess and disjoint genes. It's a disjoint gene if the connection innovation number is within the range of the other parent's innovation numbers, and it's an excess gene if it's not. Both excess and disjoint genes are normalized by dividing by the length of the longest connection genome and then multiplied by a weight value. This is C1 and C2 in the equation, and this merely sets the importance of excess genes compared to disjoint genes in the comparison and can have a value between 0 and 1. I always leave them set to 1. The final component is the average differences in the weights for connections that exist in both parents, again multiplied by a weight component, C3 in this case, which I've set at 0.5, indicating that this component is only half as important as the other structural elements in the comparison process. And what about the threshold value? Well, if you set it too high, then all the birds will belong to species 1. Set it too low, and each bird will have its own species. Both scenarios defeat the purpose of speciation. What I do instead is determine the number of species I want, say 5, and after each generation, I'll adjust the threshold to encourage the number of species being produced to move towards that number. And that's an approach that works quite well. And then you just repeat this process until all birds are assigned to a species. So you select another bird at random, which isn't in species 1 of course, that becomes species 2, and is compared to all unassigned birds, and so on. And it's this act of speciation that allows different structural solutions to be explored within a single population of birds. So now that the population has been split into species groups, I need to determine how many kids can be produced by each species. And this is done by dividing the average fitness of a species by the average fitness of the entire population and multiplying it by the number of nets in the species. So in the example shown, this would mean that the green species could grow to 6 kids, the blue would shrink to 5, and the purple would also shrink to 3. And finally, we select 2 parents from species 1 to produce a new bird. This is done by a crossover, which simply means that the new bird will take the net structure of the more fit parent, along with the connection weights for the disjoint or excess genes that it has. But the weights for genes that are common to both parents will be taken randomly from either parent. And we repeat this until all of the kids for species 1 are produced, and then we go on and do it for species 2, species 3, and so on, until the new population, the new generation, is complete. So that covers speciation and crossover. Step 6 is the same as on the last video, namely I just go through the connect genome for all the birds and modify the weights by between 10 and 50%. And that just leaves step 7, which is adding a node or connection as part of the mutation stage. Now, this is a rare occurrence. Typically, there's only a 1 to 5% chance of adding a node, and maybe a 10 to 15% chance of adding a connection during this stage, compared with a 90% chance of having a weight mutated. Adding a node is done by randomly selecting a connection to insert the node into. In the case of this generic network, the 5-6 connection has been selected to insert a node 10 into. So the first thing to do is disable the connection and add a node 10 into the node genome. We then create 2 new connections, the 5-10 and the 10-6. All the nodes are then checked to ensure they are in the right layer, and that's it. So getting the layers right is probably the most important thing to do here. If they aren't right, then calculating the node inputs will give incorrect answers and the network won't work. So for any node, the layer it should be in is linked to the longest path back to the input layer. Note that nodes can have multiple paths back to the input layer, but it's the longest one that we want. For node 6, that is now marked in green, and it's 3 steps, 6 to 10, 10 to 5, and 5 to 1. As the input layer is by definition layer 1, then node 6 belongs in layer 1, plus 3 steps, which is layer 4. Likewise for node 9, there's a direct route back to node 3, marked in red, but it's the longest route back that matters, and I've marked that in green. Again, it's 3 steps, so node 9 is also in layer 4. The output layer is always the highest hidden layer, plus 1. So anytime you add a node, you must check the longest route back for all hidden nodes and ensure they're in the right layer. And to add a connection, you select 2 nodes at random and do a sanity check. Make sure the connection doesn't already exist, ensure you're not connecting 2 input nodes, and so on. If I want to add a connection between nodes 1 and 10, I simply add that to the connection genome. As no new nodes are created in this step, there's no need to recheck the node locations. It's perfectly fine to allow connections to flow back through the network. These are called recurrent connections. So we could have a connection coming from the output of node 6 and flowing back to the input of node 5. These recurrent links allow the activations from the neurons in a hidden layer to feed back into themselves at the next step in the sequence. And this property gives recurrent neural networks a kind of memory. Okay, so if I check that function and get it to add a node and a connection every half a second randomly into a network, it looks like this. Blue connections are recurrent, and I don't show disabled connections. This method is called neuroevolution of augmenting topologies, or NEAT for short, and is used in lots of areas. They are fun to play around with. So if you're interested in this type of thing, please subscribe. In the meantime, here's the NEAT algorithm playing Flappy Birds. In this case, it's decided that no hidden nodes is the best solution.